Welcome. This presentation focuses on robust inference in finite samples, specifically delving into the theory, mechanics, and practical implementation of the Wild Cluster Bootstrap in Stata 18 and newer. This guide is tailored for applied econometricians who frequently encounter situations with a limited number of clusters, where traditional inference methods can be misleading. We'll explore why the Wild Cluster Bootstrap is a powerful technique for these finite sample settings, making advanced robust methods accessible and actionable in your research. Imagine you are studying the impact of a state-level policy on student test scores, but you only have data for 50 states, a classic finite sample scenario. The Wild Cluster Bootstrap is designed precisely for such cases. To appreciate its significance, let's begin by contrasting the ideal world of large sample theory with the common challenges of finite samples. Standard Cluster Robust Variance Estimators, or CRVE, are built upon asymptotic theory. This ideal framework assumes that the number of clusters, denoted as G, approaches infinity. Under this assumption, our t-statistics conveniently follow a perfect normal distribution, as you see in the smooth curve on the left. However, in applied research, we frequently encounter a finite sample reality. Here, the number of clusters, G, is often small, typically less than 30. In such scenarios, the distribution of our t-statistics is no longer normal, as depicted by the jagged histogram on the right. The critical issue with having few or unbalanced clusters is that our standard errors become systematically biased downward. This leads to inflated t-statistics and causes us to reject the null hypothesis far too often. This is the trap. A nominal 5% test might actually result in a false discovery rate of 15% or even higher. For example, if you're studying policy effects across 25 different countries, treating these 25 units as an infinite sample would likely lead you to mistakenly identify effects that aren't truly there. This decision tree provides a clear guide for choosing the correct inference method when dealing with clustered data. The first question is fundamental. Is your data actually clustered? If not, robust standard errors are typically sufficient for valid inference. However, if your data exhibits a clustered structure, the next crucial step is to determine the number of clusters, denoted as G. If G is large, typically greater than 50, you can safely rely on standard cluster robust variance estimators, often implemented using WCB cluster in statistical software. This scenario aligns well with asymptotic theory. Conversely, if G is small, specifically less than 50, then standard CRVE methods can lead to biased standard errors and incorrect inference, increasing the risk of false positives. In such cases, the Wild Cluster Bootstrap becomes the recommended approach. When using the Wild Cluster Bootstrap, you further consider the balance of your clusters and the exact number of clusters. If your clusters are relatively balanced and G is still within the small but not very small range, e.g. between 15 and 50, the standard Wild Cluster Bootstrap, often using Rademacher weights, is appropriate. However, if your clusters are unbalanced, or if G is very small, meaning fewer than 15 clusters, then the use of the Wild Cluster Bootstrap is essential, and specifically employing Webb weights will provide more robust and reliable inference by generating a greater variety of bootstrap samples. This slide provides a concise comparison of different inference methods available in Stata, highlighting their suitability for various data structures. Standard OLS with robust standard errors, while common, fails when data exhibit clustering because it incorrectly assumes independence of errors. The Standard Cluster Robust Variance Estimator, or CRVE, implemented as WCB cluster, is designed to handle clustering, but as discussed earlier, it over-rejects the null hypothesis when the number of clusters G is small, making it risky for finite samples. Bias-reduced corrections like HC2 or HC3 offer an improvement over standard CRVE, but they can still be unreliable, especially with extreme cluster imbalance. Finally, the Wild Cluster Bootstrap stands out as the gold standard for robust inference in settings with small or unbalanced clusters. Its key advantage is asymptotic refinement, meaning its p-values converge to the true distribution much faster than other methods, providing more reliable results in finite samples. Before running any bootstrap, it's crucial to understand your data's cluster structure. The community-contributed Stata command SumCluster is an invaluable diagnostic tool for this purpose. Looking at the output, we immediately see two red flags. First, the number of clusters, G, is only 12. This is a very small number for standard asymptotic assumptions. Second, and perhaps more critically, the cluster sizes vary wildly. We have a minimum size of 15 observations, but a maximum of 4,200. This disparity signals a high-leverage cluster, one large group that could disproportionately influence our results. When G is small or cluster sizes are so imbalanced, standard inference becomes completely unreliable. For instance, in a study of U.S. counties, if your sample includes both Los Angeles County with millions of people and a tiny rural county, Los Angeles would be that high-leverage cluster, making standard p-values misleading. Identifying these issues is the first step towards robust analysis. Now that we know how to diagnose the problem, let's explore how the Wild Cluster Bootstrap provides a solution. First, we fit a restricted model, where we force the null hypothesis to be true. For example, we set the coefficient of interest, beta, to 0. We then save the residuals from this model. Next is the wild shuffle. We apply a random weight, usually +1 or -1, to the residuals. The crucial step is that every observation within the same cluster gets the same random weight. This preserves the intra-cluster correlation. Using these randomly flipped residuals, we generate a new pseudo-dependent variable, which we can call y star. The formula is shown on the slide. Finally, we regress this new y star on our independent variables, calculate a t-statistic, and save it. We repeat this process, the shuffle, the pseudo-data generation, and the re-estimation, hundreds or thousands of times to build an empirical distribution of t-statistics, which we then use for inference. This slide highlights a crucial theoretical choice in the Wild Cluster Bootstrap, whether to impose the null hypothesis during the bootstrap process. The recommended approach is the Wild Cluster Restricted Bootstrap, or WCR. This method imposes the null hypothesis, meaning it generates bootstrap samples as if the null were true. This theoretically superior approach leads to better p-values and provides what is known as superior asymptotic refinement, essentially converging to the true distribution much faster. The alternative is the Wild Cluster Unrestricted Bootstrap, or WCU. This method does not impose the null hypothesis. While it has its niche uses, primarily for complex nonlinear hypothesis tests, it generally leads to a loss of statistical power, making it harder to detect true effects. A fundamental assumption for both methods, and for any clustered inference, is that errors are uncorrelated across clusters, but can be arbitrarily correlated within each cluster. When performing the Wild Cluster Bootstrap, a crucial decision is selecting the right type of random weights to apply. We primarily consider two options, Rademacher and Webb weights. Rademacher weights are the default and simplest choice. They represent a two-point distribution, where each residual is multiplied by either +1 or -1 with equal probability. This approach is effective when you have a moderate number of clusters, typically greater than 15. However, a significant limitation arises with very small numbers of clusters. With Rademacher weights, there are only 2 raised to the power of g unique combinations of weights possible. For instance, if you have only 6 clusters, this translates to just 64 unique bootstrap samples, which is often insufficient to build a reliable empirical distribution. This is where Webb weights become essential. Designed for scenarios with very small numbers of clusters, specifically when g is less than 15, Webb weights offer a 6-point distribution. This dramatically increases the number of unique bootstrap samples that can be generated, providing much more robust and trustworthy inference, even when your cluster count is extremely low. The choice between these two weight types is critical for ensuring the validity of your bootstrap results. Stata 18 introduced the official Wild Bootstrap command, providing a seamless and integrated way to perform the Wild Cluster Bootstrap. As a prefix command, you simply place it before your estimation command, such as regress. The syntax is quite straightforward. You specify your regression, indicate the clustering variable using the clustering option, and then add bootstrap-specific options. Crucially, always set a seed with rseed for reproducibility. The number of Bootstrap replications is controlled by reps of. While the default is often 1,000, higher numbers are generally better for publication. For error weight of, you can choose between Rademacher, the default, or Webb, a decision we discussed earlier based on your number of clusters. This command is very efficient for linear models and readily supports regress, regress, and fixed effects xtreg. While Wild Bootstrap is excellent for many standard cases, for more advanced applications, there's a powerful community-contributed alternative we'll look at next. While Stata's native Wild Bootstrap command is excellent for many cases, for more advanced and complex needs, the community-contributed boot test command is the power user's toolkit of choice. Developed by Rudman and his colleagues, boot test is a post-estimation command, meaning you first run your standard regression, like the regress command shown here in step 1, and then you apply boot test in a second step. It's easily installed via ssc install boot test. Boot test offers several significant advantages. It's often much faster thanks to optimized MADA algorithms, and its scope is much wider. It supports instrumental variables, generalized method of moments, and even multi-way clustering, capabilities not always found in the native command. Furthermore, it can generate powerful visualizations like confidence curves. As you can see in the example, you simply run your initial regression, then follow up with boot test, specifying options like the number of repetitions, the type of weights, and a random seed for reproducibility. This command gives you powerful, flexible inference for even the most challenging cluster structures. For our lab exercise, we're using the well-known NLW88 dataset, which contains wage data for young women. Our primary research question is to estimate the effect of job tenure on wages. We anticipate that errors might be correlated within the same industry, so we've decided to cluster our standard errors by industry. A quick look at the tabulation of the industry variable immediately highlights a critical issue. We only have 12 distinct industry clusters. As we've discussed, this places us firmly in the danger zone, where standard asymptotic inference methods are unreliable and can lead to misleading results. Given that we have fewer than 15 clusters, our previous roadmap tells us that we absolutely must use Webb weights for our Wild Cluster Bootstrap to achieve robust inference. This crucial preparation step helps us diagnose the problem before we proceed to estimation. First, we run a simple regression with standard cluster-robust standard errors using the cluster industry option. The output looks fantastic at first glance. The coefficient on tenure is 0.22, and the p-value is 0.000. This suggests a highly statistically significant positive relationship. However, this result is misleading. With only 11 degrees of freedom, g-1 equals 12-1, the t-distribution is not well approximated by a normal distribution. The tiny p-value is an artifact of the downward bias in the standard error. We should not trust this result. A researcher new to these issues might see this output, conclude that tenure has a strong, significant effect on wages, and publish the result. This could be a false discovery, driven entirely by using the wrong statistical method for the data structure. Now, let's apply the correct method and see how the inference changes. Now we apply the correct procedure using the Wild Bootstrap command. Crucially, because we have only 12 clusters, we specify error weight Webb, aligning with our earlier discussion on appropriate weighting. Let's compare these results to the naive approach. The point estimate for the coefficient on tenure remains identical at 0.22, as bootstrapping does not alter the coefficient itself. However, the inference changes dramatically. The bootstrapped standard error is now much larger, leading to a t-statistic drop from 6.95 to 2.82. Consequently, the p-value increases significantly from 0.000 to 0.042, and the 95% confidence interval widens from roughly 0.12, 0.32 to 0.01, 0.45. While we still reject the null hypothesis at the 5% level, our certainty in this rejection is considerably lower, and the estimated effect is much less precisely determined than the naive approach suggested. The boot test command allows us to generate a confidence curve, which provides a powerful visual representation of our bootstrap results. This curve illustrates the p-value associated with every conceivable null hypothesis regarding our beta coefficient for tenure. The robust 95% confidence interval is precisely the range of beta values for which the p-value curve remains above the critical 0.05 significance level. Consequently, any null hypothesis where the curve drops below the red line can be visually rejected. It's important to observe that the peak of the curve corresponds to our point estimate, and the curve itself is not perfectly symmetric. This asymmetry is why the resulting bootstrap confidence interval is also not symmetric around our point estimate, providing a more accurate reflection of the true uncertainty. A critical edge case arises in difference in differences, or DID, models when you have very few treated clusters. For example, imagine a policy that is implemented in only one state out of 50. In this case, the standard Wild Cluster Bootstrap fails. The restricted version, WCR, will tend to under-reject the null, losing power. The unrestricted version, WCU, will tend to over-reject, producing false positives. The solution for this specific problem is more advanced. It involves methods like subcluster bootstrap, where you might cluster at the state level, but bootstrap at a lower level like the county, or specialized techniques like farthest neighbor methods. If you are studying the effect of a new law passed only in California, you have 49 control clusters but only one treated cluster. Standard WCB is not reliable here, and you would need to explore these more advanced fixes. First, always begin by checking the number of clusters, denoted as G. A simple tabulation of your clustering variable will give you this crucial information. If G is less than 50, you should actively plan to employ the Wild Cluster Bootstrap for robust inference. When G is particularly small, specifically less than 15, it is essential to use Webb weights for your bootstrap. For larger G values, between 15 and 50, the default Rademacher weights will suffice. To ensure the replicability of your research, always remember to set a random seed for your bootstrap procedure. By default, opt for the Wild Cluster Restricted Bootstrap, which imposes the null hypothesis, unless specific circumstances dictate otherwise. Finally, for full transparency and to illustrate the robustness of your findings, it's best practice to report the Wild Cluster Bootstrap p-value alongside your standard cluster robust variance estimation results. This allows readers to understand the sensitivity of your inference to the chosen method, enhancing the credibility of your conclusions. We've covered a lot of technical ground today, and for those who wish to delve deeper into the methodologies and theoretical underpinnings of the Wild Cluster Bootstrap, this slide presents key references. The foundational work by Cameron, Gelbach, and Miller in 2008 provided significant advancements in bootstrap-based inference for clustered emmers. For practical implementation in Stata, the article by Rudman and colleagues from 2019 introduced the powerful bootstrap command, which we explored earlier. McKinnon and Webb's 2017 paper is crucial for understanding how to handle situations with widely varying cluster sizes, influencing our choice of bootstrap weights. And, of course, the official Stata 18 manual provides comprehensive documentation for the native wild bootstrap command. These resources offer excellent avenues for further study and practical application of robust inference techniques in your own research.